So thank you for the introduction. Thank you for the invitation. As usual, I wish I could be back in person at UCLA. I spent a lot of time there, really enjoyed the campus. But today we'll do this talk remotely. So mm, I'll talk about two main topics today. One is how to train machine learning models when you have very few label data available. And the utility of doing this is easy to appreciate. You may have enough data about frequently occurring categories, cars, cats, dogs, and planes, but you may not have data about the particular incident that your autonomous car saw yesterday on the road. And we would like to understand how to make machine learning models work well quickly on these new situations. The second kind of topic I'll talk about is how to understand interaction in autonomous driving, which we believe is one of the key hurdles in uh, how we may deploy autonomous vehicles. To begin, I'll give you a brief overview of some of the work that I have done in autonomous driving over the last years. I This began really as an effort to understand multiple agents in the vicinity of your cars. This was work that we did in Singapore back in the day now, around 2012, 2013. This was a project where MIT was trying to build, in this case, an autonomous golf cart, among the first autonomous vehicles outside Google at that time. And this golf cart, through a combination of cleverly implemented filtering, cleverly implemented online POMDP algorithms, some of it was our work. It was able to interact work in challenging situations. So about 20 people walking in your vicinity, trying to solve a PUMDP for intent prediction of where they would be in the next step. You know that people are not arbitrary random variables. They have certain inertia, and that is what you use to help yourself when you solve these online PUMDPs using point-based methods. And you can do it reasonably well. The car wouldn't go very fast, but it was safe. The next kind of challenges that we were interested in solving was, how do you take urban vehicles and make them understand the same rules of the road that humans have bigger drive by. So you have the driving manual, and what you would like to do is not just do motion planning of how to go from point A to point B, but also do motion planning in a way that understands the rules of the road. What are safety rules? What are cardinal rules that you will never ever wish to break, etc. And typically, these rules in control are modeled using temporal logic. Temporal logic is a subset of first order logic, which will tell you that given a temporal sequence of predicates, whether this sequence satisfies a particular rule that says do not ever break a stop sign or do not ever go beyond 20 miles per hour when you're traveling on the road. And these are rules that are easy to formalize to an extent, so long to the extent that the rule book is consistent. Typical driving manuals are, we found out that they are not consistent with each other, but that is a different conversation. Given these rules, you can design motion planning algorithms that give you dynamically feasible trajectories even for differential dynamics, like that of a car, and also give you provable safety. But that doesn't take you all the way there, right? Because while driving, you are bound to come across situations where you will have to break these rules in order to make progress. Now, if you really want a provable guarantee of safety from an autonomous car, uh, you need these rules in the picture, but then that will hurt you if you want to make progress. So you need to design logics that straddle the balance between a concrete safety certificate coming from, let's say, linear temporal logic, but the ability to also remove some of the rules in your rule book and make progress in an event where you are stuck. This is what we call minimum violation logics. They basically have a hierarchy of rules. Let's say the first rule that you would never ever dream of breaking is do not hit a human being. The second rule would be something like do not do not go into an incoming lane. But sure, you are happy to break the second rule if you are traveling on a single lane road in a crowd in one of these kind of situations. These are what are called minimum violation logics, and they actually changed the game completely. So they changed the game from being able to do chance constraints, being able to do generic motion planning for autonomous driving, to be able to for you to be able to get some certificate of how safe you are modulo these rules. This work really began in Singapore. As I said, we were dealing with small autonomous vehicles, golf carts in that area. It matured into what is called Autonomy today. It's a company that was spun off from MIT around 2013 and 2014. Today, Autonomy is quite big. They have successfully demonstrated that they can travel in Singapore. They also operate in Boston and Las Vegas, and under fairly challenging situations across a wide fleet of vehicles. They took the minimum violation work much deeper. So basically, the rule book that they operate with is much, much wider than what we were doing in an academic setting back in 2013. The place where I begin today is really trying to answer the question. Yes, we have developed some algorithms that work at scale for autonomous driving. What can we not do? It is very apparent over the last 5-6 years that yes, we have become good at motion planning. We can do safe motion planning decently well in urban scenarios, but what we really lack is the ability to understand perception. That is what got me personally into machine learning for my PhD. So what we just talked about was most of my master's work. And during my PhD, I was studying neural networks, how to make neural networks work well from an optimization perspective, understanding the energy landscape of neural networks, coming up with better training algorithms for neural networks. And in the last 1 or 2 years or so, we've been digging more into how to make neural networks work well with few labeled data. So in the next 10 minutes or so, I'll talk about how to make models work well with new data. And in the remainder of the time, I will talk about a different problem of interaction in autonomous driving. So this is Stan Osher's land. So I will use his trick of changing different slides. So I would contend that there are really 3 regimes of classification. The first one is something that we are very familiar with, the high shot regime, where given, let's say, 100 to 1000 samples per class, we are fairly good at training neural networks today. It is these samples come from specific kinds of categories, cars, cats, dogs, and plain stuff that you may be interested in at a generic level. For special situations, in this case, I've shown an example of one case where one may want to classify the produce that is grown on their farm. This is a prototypical image classification problem, slightly different from driving, but the idea is you don't have too much data from these problems all the time. It is very easy to imagine problems in medical imaging where you may not have labeled samples. And the key to doing good machine learning in the low shot regime is for you to be able to build a rich representation. And we are lucky that neural networks are a good way of learning rich features from the high shot regime. So fit a model on cars, cats, planes, and dogs, and try to adapt this model to new classes with few data from the new classes. This is what is called few shot learning today. And you can also take it all the way down to the anomaly detection regime, where you have only one sample per class or one incident that you saw when you tested the model yesterday. In the world of robotics, this takes a slightly different form. You would like to think of a robot trying to solve multiple tasks. So in this case, let's say, imagine manipulation to be concrete. And these tasks can be a little pedantic. Let's say pick up a cup and saucer, pick up a football, pick up spoons and forks, etc. From a more practical perspective, they can also come in the following form. So if I have a robot manipulator policy for picking up objects that are trained in my lab, can I adapt this policy to a slightly different setting? If my assembly line in the factory changes by a tiny bit, can I adapt my policy quickly to the changes and make sure that it still performs well? There's a third kind of domain where you would like models that adapt to cases when your sensor count off, where your sensor started degrading. whether your driving policy is suddenly working under bad lighting. And this is the utility of adapting both classical image classification style models, or also reinforcement learning policies with little data on new situations. The moral of the next few minutes will be that the high shot regime is easy. We know how to do it fairly well. We are going to look at the low shot regime. The problem formulation in few shot learning would typically be like this. So I have a large set of data that I collected from frequently occurring tasks. And I would like to, 1 second, let me annotate. Yeah, I would like to learn features on these frequently occurring categories and then modify these features to new tasks. In this case, let's say strawberries grown on a farm. What do I have to do this? I have a few new classes, let's say 3 kinds of strawberries, which is called ways in this literature, W. And I have a few labeled samples from these new classes, let's say 5 labeled samples or 2 labeled samples from each of this class. And when people say few shot learning, what they really mean is that the number of labeled samples from the new classes is small. The number of samples from the old classes, it can be very large, because these are after all frequently occurring classes. It's easy to get that kind of data. To give you one flavor of how current algorithms for adaptation work, here is what I'll do. So you know that you're not going to be tested on cats and cats at test time. So instead of trying to be a good classifier for cats and cats and cats, it is much nicer to think of this problem as a clustering problem. What you want is to learn features that can cluster, that you can cluster easily. And this is what typical models like prototypical networks would do. If you have learned a good feature space where similar classes end up close to each other in the feature space, then even if I show you totally different classes, you can imagine that the neural network is good at discriminating against different categories, even if it doesn't know the names of those categories. So the features belonging to class C1 will all be close together. The features belonging to class C2 will all be close together. And now you can easily design, let's say, a mixture model style loss to classify a new datum X across new classes, not necessarily the old ones. So this is how typical algorithms work. They're basically some form of pre-training to be done to learn this feature space, and then all the approaches from metric learning being used to classify this feature space. The moral of the story is that they don't work really well. Few shot learning, or every single time you try to adapt a model to new situations, there are many different kinds of new situations. In this case, for image classification, even if I show you adapt a model to 3 different kinds of strawberries, the model may not perform well to adapt to 3 different kinds of mangoes. So the diversity of other tasks is insane, and that is what gives these that is what is challenging when you try to adapt models to new tasks. The typical error bar, so this is a box plot of a few algorithms. The algorithms are on the x-axis, and the y-axis is accuracy on a task. Let us not worry about what task it is, but it's one of the benchmark tasks in this literature. The standard deviation of these algorithms is about 50%, more than 50% in a lot of cases. And that really tells you that even if I am good at solving some tasks, let's say some of these tasks get an accuracy of about almost 80% for prototypical networks, there will be other tasks for which I do extremely poorly. And this is not a failing of the current algorithms. This is really a fact. This is really a fundamental property of the problem that we have. Adaptation is difficult because there are many different corner cases, and this is what this kind of a plot is showing. The key idea that we have is basically to avoid thinking of adaptation as a clustering problem and really think of adaptation as a fine-tuning problem, as a transfer learning problem, where the idea is that if you learn a machine learning model on your frequently occurring tasks, I think of this machine learning model as some parameters that I've learned on my training data set, but really you should think of this as a function that takes in your training data set, and it is in charge of predicting on a new label. Now, X need not belong to the same, need not have the same categories as your training set, but surely you're allowed to search over the space of functions that are both that have 2 arguments, one of your new test datum and one of your entire past training data set. And this is what brings in ideas from what is called transductive learning, where you can adapt a model to do well on a new task if you have some unlabeled data from the new task. So the key is to be a little more pragmatic and think of this as simply fine tuning, where I'll take my parameters theta star and I solve a new optimization problem at test time on the target task on the new on the few labeled samples from the target task to classify not only the new samples correctly, but also have other terms that belong to my training tasks. So my model is not allowed to go very far away from my training task, because after all, that is my foundation for learning the representation. But I'm explicitly doing fine tuning instead of clustering on this new labels. I'll not worry about this. To summarize, here is how it looks. So consider an example where I have 5 new categories. These 5 categories are shown by these 5 different colors. When you explicitly adapt a model, you will see that these crosses are my labeled data on the new tasks. These translucent circles are my new test data. So there are the 3 different kinds of strawberries, or 5 different kinds of strawberries in this case. If I were to simply cluster my new data, I would get a very poor clustering, because I haven't managed to learn a good feature space that will allow clustering of new data, presumably because my training tasks weren't very related to my test tasks. But if you do explicit fine tuning, you will have a situation where the unlabeled data actually moves towards the labeled data, because we are adapting the entire neural network along with these unlabeled samples. And now it is very easy to define a clustering loss. Of course, you will make mistakes because you don't know the labels of the unlabeled data, but the mistakes will be very few, much fewer as compared to a generic clustering loss on the translucent circles. This works well. So these are some benchmark problems on which we have tried, and roughly speaking, it works much better than other clustering based approaches or other transduction based approaches for few shot image classification. We also tried it on much larger problems. So this is the ImageNet 21K dataset. It has about 14 million samples, 22,000 classes almost. And it's a very natural dataset to think about rare classes and frequent classes. The first few, the blue region, are all the classes that are very frequent. The green region are all the classes where you don't have too much data. So the y-axis is the number of images per class. So you have less than 1,000 images in the green region. So you can train models or pre-train models on the green part, and then try to adapt them to subsets of the green part to test how well they do. And they actually do very well. So you will get accuracies that are as high as 90% on 5 new classes from the green region, provided you do a good job of training on the blue region. And that is quite surprising. That tells you that the more diverse data you have for your pre-training, the better you are going to be when you adapt. Okay. We have a few more theoretical tools that we've used to analyze this. So if you are so good at transferring representations to new tasks, there has to be a limit where this breaks, right? There has to be a limit where there has to be some theory that tells you when you can do a good job of transfer and when you cannot do a good job of transfer. When is the target task close to the source task and you can get away with simple fine tuning, and when you need some special tricks. So we've in a recent paper at ICML, we've basically devised a set of tools that draw from information theory and thermodynamics to understand when 2 tasks are close to each other, how you can design good transfer learning algorithms that let you go from a source task to the target task. I will not talk about this, but I just wanted to mention, you can read the paper. It is on archive if you go to my website. What I will talk about next is understanding interaction in autonomous driving. So this is changing gears. This is a problem that I started working on thanks to a student who did her master's thesis with me. So this is entirely her conception of the problem and her work. I played an advisor's role in this case, not too much of a technical role. So the the motivation for solving this problem is that you really are the key hurdle to doing a good job of driving in an urban environment is that you don't know good models for what the other agents are going to do. If you knew good models for other agents, then yes, you can design good forecasting models, and now you can do planning. The current way we do it to an extent is that we know, let's say, up to the extent that we understand the environment around us using our sensors, we imagine a quasi-static environment. And now, given this quasi-static environment, some rudimentary form of forecasting that you may do for the next 2 to 3 seconds, you will predict, you can plan a trajectory for your car. This doesn't work that well because it is inefficient. It doesn't work that well because you may make mistakes in how you forecast the vehicles around you, and that will lead to you being unsafe. The key thing that prevents you from doing good forecasting is that you don't understand how different agents interact with each other. How does my motion influence the motion of some other vehicle? And this is kind of this is something that happens so naturally when you and I drive. When you are at a four-way stop sign, you definitely make eye contact and decide if there is some ambiguity as to who came first. These are the kinds of behaviors that we would like to build inside agents. And the motivation for this work was that you will see often in the Bay Area where Google will test their cars pretty frequently, that it is almost a tradition to be antagonistic to an autonomous car. You will see people coming in front of an autonomous car because you know that the car is designed to be as safe as it can be. So you know that it is never going to be aggressive towards you. Now, this is a reasonable, this is just a societal thing. It is happening. How can we fix it? So the way we fix it is by making people understand that autonomous vehicles drive in a certain way. The most natural way for autonomous vehicles to drive is to mimic how humans drive. So if I come to a stop sign and I creep forward a tiny bit to take initiative to in this interaction, I would like autonomous agents that also have this flavor in their policies. I don't want to sit up in situations where I'm waiting for everyone in my vicinity. I'm being super safe here, but I am not making progress very quickly. Okay, so this is exactly the situation that we would like to handle in this approach. Instead of, we chose to be very pragmatic about how to understand this problem. And instead of kind of going towards simulators like Carla or other ones, flow-based simulators, which may not take you, which may not tell you a lot about interaction, because there are other challenges with using the simulators. That is, it's more of a representation learning problem when you create a policy or you create an algorithm that drives well in Carla. So we created a very basic simulation platform where you have roundabouts, where you have corners, you have straight lines certainly, and you have an ego agent, which I'll denote by cyan. That is driving in this very crowded environment. So this ego agent typically in our experiment has 15 to 20 vehicles in its vicinity, and we would like to study how it interacts with these vehicles. The task is to travel to a randomly assigned goal region in this lane map and avoid collisions, of course. A key one that we would like to check is whether you halt traffic around you because you made a mistake. And of course, you should be able to reach the goal safely. All the other agents run what we call is an oracle planner, and we'll dig into this a little bit in the future. This oracle has global information about the agent's future. So think of this as all-knowing agents which know exactly what the other car is going to do, but the ego doesn't have this information, it is privileged. The central theme of understanding interaction is that it is very easy to be safe in autonomous driving. You just don't move. You're extremely conservative. You wait for everything around you to clear up, and you will be fine. You're safe. You're not very efficient. If you want to be a little more proactive in how you tackle interaction, you need some notion, some model for how aggressively you would like to drive. And this is both an attempt to model a natural human being's way of driving, but it's also trying to give you the ability that once you have, trained a policy to drive in an environment like this, you should be able to tweak this policy, right? So let's say I train a model, I give it to Google to drive their car, and suppose they find this model to be too conservative or too aggressive. We would like some tunable knob on this policy that lets them detune the aggression to make it safer, or tune the aggression higher up to make it a little more proactive. So that is what we would like in our policies. We want to model aggression. Interaction is not very meaningful if you don't model aggression. So here are the goals. We would like policies that can handle arbitrary number of agents in your vicinity. This is not that common in the literature on interaction. You would like to learn these policies without making explicit assumptions on what the dynamics of other agents are. And this is an important point because it is not very easy to guess the dynamics of other vehicles around you. If you are looking at sensory data of a motorbike or a small car or a big car or a sedan or a bus, these are two totally different dynamics, and it's often very difficult to design estimation algorithms for what even the type of a car is given its dynamics. You can use modern methods. In this case, we use off-policy reinforcement learning methods that are sample efficient, that precludes having to run this policy many times in these challenging environments. Multiple agents is a very stochastic environment, so it's not very easy to gather good episodes with it. But off-policy methods do allow you to take a data set and study it a little more thoroughly than what on-policy reinforcement learning methods would allow you to do. It is not that easy to do it in these problems because there is a lot of stochasticity in the environment inherently, and you have to be very systematic about how you run these experiments. And that brings me to the third point, the third contribution, which is we would like some systematic platform to study interaction. We are not interested in making it photorealistic. We are not interested in simulating LiDAR data out of it, but we would like to study this one modality, which is interaction. And the goal is a little pedantic, if you will, but if we are successful in doing this, we should be able to quantify the influence of the ego agent on its environment very quantitatively, instead of coming up with a couple of videos that show that it works well. We use in this paper what is called attention. Now, attention is a very popular thing in the deep learning world these days. At its heart, it captures correlations between different inputs. Typically, you will see attention written using these three quantities: queries for Q, K for keys, and V for values. And the nomenclature comes from natural language processing, but the idea is that if I have a certain query vector, I would like to see which one of the keys it most correlates to, and then pick the values that correspond to those keys. Imagine it as a dictionary, pick the values that correspond to those keys, and that is a notion of that is some weighted combination of all the keys in my dictionary that my query is giving me. It has its roots all the way back to the 50s in classical density estimation or classical kernel-based methods. If you are regressing a function, let's say the green function in this case given by your from where you sample your data, and I would like to design, let's say, a kernel density estimator for regressing this function, my estimated value f of x is simply a sum of my target, my labels yi, or my targets in regression yi, times a factor, times a scalar factor, which is, let's say, the kernel, how well my data x, my input x correlates to the data, one of the data points that I have in my data set. So nothing special about it, just a weighted combination of the outputs. And this has been kind of reformalized into attention in the modern deep learning literature to do interesting natural language processing tasks. We'll not worry about how the architectures look. They're a bit complicated, but at the heart, they are basically using attention. Some of you may have heard of this work called social attention, which takes exactly this model an attention-based transformer and tries to learn a queue function for driving in interaction scenarios. So in their case, it is easy to understand. The query is the ego state. Key and value are the states of the other agents. So social attention is asking the question, is my ego state similar to the state of some other agent? Yes or no? If it is, then I'm going to use a policy. I'm going to take the control action that the other agents took. Questions?
Oh, 10 minutes.
Yeah, thank you. So in this business, you want to be a little more careful about how you encode the driver type, the aggression of the driver, and we basically encode it using a different multi-layer perceptron instead of clubbing it together with an observation, because it lets us keep the driver type, which is a single scalar real valued variable, whereas the observations is a large vector of all the states of the cars in your vicinity. It lets us keep the driver type a little distinct in the model. Otherwise, you would overwhelm, the driver type will get overwhelmed by the observations. In terms of the technique to do this, we use off-policy reinforcement learning algorithms that involves minimization of the single step squared temporal difference error. If this is your Q value, which tells you the average return that you're going to get if you execute a particular policy all the way into the future, it is dependent on two variables, which is the observation that your ego agent gets at time t and the control that your ego agent can take at time t. And this is simply the Bellman residual. You're trying to minimize the Bellman residual, the squared Bellman residual, and any policy that achieves zero Bellman residual is the optimal policy. In this problem, you can use a few tricks, which we've discovered over the last couple of years on off-policy learning. Typically, when you do deep off-policy learning, computing what the second Q function is, the Q function at time t plus 1 is very tricky, because you don't know a good control action to plug in here. If you take the maximum control action, you cannot do it because you're doing continuous actions. If you fit a policy to take the control action, then it really depends on how well you fitted the policy, etc., etc. But handling the target, the so-called target in reinforcement learning in the temporal difference term, is a very challenging thing. And in this case, you can kind of use two Q networks and take the minimum of them to use as the target. And that really helps. This is a new trick, but it's a trick nevertheless. Another little thing is that you can train multiple Q functions and simply take the best policy that they entail as the policy when you evaluate your model. I'll not go into this, but the summary of how the Oracle Planner works is that it knows the trajectories of all vehicles in your vicinity, and it asks the following question. If I stop and you go, is it better that I go and you stop? If the second one is better, if I go and you stop is better, that doesn't lead to collisions, then I'm going to stop. Otherwise, I'm going to go. And this is basically a tie breaking. You can do a little bit of tie breaking after this, but the Oracle policy is designed to be as safe as it can be, because it has information from all across the board. You can also design other policies that act as good baselines, and they're also quite performant, surprisingly. A simple car for policy, which always maintains a specific distance to all the cars in front of you, and does not try to be too aggressive. The data in these problems is kind of the key hurdle. So if you simply take a set of generic episodes and try to study how interaction happens in generic episodes, this is very unsatisfying, because it's a very large multi-agent environment, and it's very difficult to come up with interesting scenarios, enough number of generic episodes where you're going to see non-trivial interaction. So we do hard mining of good episodes. You certainly have generic episodes because they are the baseline of how your model will work in a generic situation, but we explicitly design collision episodes. We take all the agents, all the plans of the agents using the Oracle Planner, and design episodes where these agents will collide against each other. These are what are called collision episodes. They're very hard. Interaction episodes are even harder to curate. but you can do it because you know the explicit plans. Essentially, when two cars come within some radius of each other, we call it an interaction. And we explicitly curate these kinds of episodes and add them to our data set. So during training, you want to train on all three different kinds of episodes, but during testing, now you have a choice. Do I test on only generic episodes? Well, no, then you won't be studying interaction. So what we do is we merge together some generic episodes and some interaction episodes as the validation and test sets. You don't really care for the collision episodes. These collision episodes are the episodes where there is only one possible answer that the ego stops. Otherwise otherwise you're bound to collide. Let's say someone is trying to bump you from let's say you are heading into someone and stopping is the only option. So the summary of our experiments in this direction is that you can, because you are doing of policy reinforcement learning with high capacity models, you can be generalized to different road geometries and still do a good job of driving safely and efficiently. You can tune the aggression of these policies to give you different kinds of behaviors, such as cautious driving or being more proactive in taking the initiative. It is also robust if you change the policies of the external agents, and it is certainly efficient and safe. To give you a few examples, here is how we study it. So we want three kinds of metrics. The first metric is how many times do you collide against other cars, which is collision. The second kind of metric is how many times do you fail to reach the goal, which we call timeout. Now, this is really not that important in terms of interaction, because if you ever implement a reinforcement learning based policy on a real car, you will use it only as a prior for some other motion planning algorithm. It's unlikely that you will directly undertake the actions given by this policy. So timeouts being large doesn't really hurt you in driving in a practical scenario. The third metric that we designed is what is called the time to finish, which is how quickly do you get to the goal region. And of course, the Oracle is very good on all these metrics. So it takes, let's say, about 65 time steps in this case to reach the goal. It has collision and timeout rates of basically 0. And that's not surprising. It knows all information about the environment. If you simply do a generic neural network, a multi-layer perceptron on this problem with this data, you are going to get reasonable performance, but you will have a large amount of collisions, about 3 to 4% collisions in this case. Because you're using attention, and this is an algorithm called MIDAS, which is our algorithm, you reduce the number of collisions while only marginally increasing the timeouts, the blue region in this case. And this persists across the two different kinds of test episodes, one where you're only testing on generic test episodes, and the second, in this case, you're testing only on interaction episodes. The interesting part of attention is that even if you have 20 vehicles in your vicinity, your policy doesn't have to depend on all the states of the 20 vehicles. The attention module automatically captures only the agents that are relevant to you making your control decisions. And you can check this after training by looking at the attention maps. But it gives you a natural notion of what are the other agents that affect your decision and whom you should affect to begin with. You can also show that it generalizes to different policies. So in this case, you can add a little bit of noise to external agents and show that you're still consistent. You're still consistently driving safely and efficiently as compared to, let's say, the Oracle in MIDAS. The key question that we want to study was, of course, interaction. So now that you can drive safely, let us see how it interacts with other agents. And the x-axis of this plot is a little difficult to understand. So it is the time by which the other agents precedes you. So if it precedes by a time of 1.5, that means that it came before you by 1.5 seconds. If it preceded you by a time of 1.8, then it came before you by 1.8 seconds. In those cases, you are happy to wait. So the the control action of the autonomous car goes down, so it is waiting as it goes down. The pink region is exactly the region where interaction is happening and non-trivial interaction is happening. So you can show that they are safe in these kinds of regions. And at its heart, doing a good job of interaction boils down to you moving this 0.3 a little bit closer to 0, you moving this 1.5 a little bit closer to 0, because you want to interact non-trivially but still make progress. So this is an experiment. I will not go deep into it, but we've tried these kinds of policies on different scenarios. So T intersections, roundabouts, we are in the process of trying them out in more realistic road geometries. Let's say the city map of the area around Penn, and see how these policies drive after being trained in simulation. But they look something like this. So in this case, notice that the cyan car at the top, it is waiting because it sees an incoming car on the left-hand side, and this is the proceed cautiously, but take the initiative if the other car halts even a tiny bit behavior. The next example I would like to show you is this. So notice that this is a busy roundabout and the ego agent is trying to enter this roundabout. Now, in this case, you have to be a little more aggressive in how you take initiative, and you're still getting this behavior. So we've studied these kinds of interactions using these mind episodes, and we can show that this if you did not learn an interaction policy, then you would not be able to drive safely in this interaction scenarios. To summarize my talk, we really talked about two different kinds of problems. The first one is how to take machine learning models and adapt them to new data. And adaptation comes in various forms and guises. The simple thing that we did about adaptation was simply to fine-tune your model on new data. This works. This works if the new task that you're solving is close to you. But the challenge is to kind of move beyond classification and really talk about decision making. So classifying strawberries and mangoes is one thing, but making a model adapt to a slightly different cars, let's say if you trained your policy in the US, adapting it to drive in Singapore is a totally different ballgame. The second part of the talk was study of how interaction happens in urban driving. And the moral of the story is that reinforcement learning offers you a good way to study interaction. Now you would like to see whether this really scales to real world platforms. So we would like to do experiments on real autonomous vehicles and see if they have, if we can execute these policies safely within the limits of our testing. That is all from me, and I will take questions now.